Okay, good morning. Welcome back, lads and ladies, to Calc 2. Last time we introduced section 7.2 on integrals of trigonometric functions, focusing specifically on powers of sine and cosine, or powers of secant and tangent. We did not get to talk about everything, so of course we're going to pick it up there today. Let me turn on the screen share. Get the document camera talking to us. We will begin. Thanks, Amanda and Katie, for turning on your cameras. I'd just like to remind everybody, if you are somewhere you can turn on your camera, please go ahead and do so. It's a big help to me. Let's see here. Close the blinds. Some consistent lighting. And all right, here we go. So this is MAC2312, section 004, which is Calc 2. And the date today is the 26th of January, 2022. Today we're going to finish section 7.2 on trig integrals. And then we're going to begin section 7.3, which is on Trig Sub. And if those things sound like they go together, well, that's because they do. Trig integrals we are familiar with, integrals of trig functions. Trig sub is where you take an integral that does not have any trigonometry in it, and you make a substitution which introduces trigonometry into the problem. So the things that we will kind of be arriving at after doing the bulk of the work in section 7.3 will be 7.2 integrals. All right, so in 7.3, we're going to be given some gnarly integral. We're going to do something to it, and the result is going to be a 7.2 integral. So I don't want to waste any time. Last time, we said that if you're integrating some power of sine, like sine to the m of x, times some power of cosine, like cosine to the n of x dx, we're going to consider two different cases. If at least one power is odd, then we're going to do a U sub. Right? And the way that that U sub works is you grab one copy of the odd powered function and set that aside with the dx. The idea being that you grab one copy of the odd powered function, set that with the dx. That's what's going to get canceled when you make your substitution. What will be left will be even powers of that function. So you rewrite the remaining powers in terms of the other function, then sub u equals that other function. All right, this was the strategy that we discussed last time. The other case that we need to consider is if you're not in this case, right? If it's not the case that at least one of the powers is odd, that means both of the powers are even. In this case, we just beat the thing to death with half angles to death. Beat the thing to death with half angle identities. And if you look at your notes from the other day, I gave you a list, a big list of trig identities that we're going to use in this section. One of those families of identities were half angle identities for sine and cosine. So I'm going to begin here by looking at one of the cases where the powers are both even. Or maybe we'll look at an integral where there's an odd power to get started. All right. So yeah, this is the thing. Let me remind you what those half angle identities say. Cos squared theta is 1/2 times parentheses 1 plus cos of 2 theta, and sine squared theta is 1/2 times 1 minus cosine of 2 theta. And it is a good thing that they both end in cosines. That's what we want. This is actually a positive. And let's not waste time. Let's not waste time. So we saw examples like this. I know. Saw examples of case 1 yesterday. Let me just begin with case 2 stuff. All right. So yes, you cute kitty. So let's evaluate the integral of cos squared x times. Oh, let's just do cos squared x on its own. All right, so here it is a sine cosine integral, and both powers are even. The power of sine is 0, which is an even number, and the power of cosine is 2, which is of course an even number. So the only thing to do here is use the half angle identities. Both powers even, which means you should use half angles. So the half angle identity for cosine is cos squared is 1/2. The variable here is x, not theta. So it's 1/2 times 1 plus cosine of 2x. I still have my dx at the end. The 1/2 can pop out. And what's left is just the integral of 1 plus cosine of 2x dx, which is not difficult. The integral of 1 dx is just x plus the integral of cos 2x is a micro u sub, right? You would sub like z equals 2x. This would be 1/2 integral cos z dz. Integral of cos z dz is sine z, so this is going to be sine of 2x over 2. And we discussed the kind of common micro u subs that you need to be comfy with here. All right, so this would be a perfectly acceptable answer for this problem. It is maybe worth noting that if you want to, you can simplify the sine of 2x using a double angle identity. Sine of 2x is 2 sine x cos x. So this is 2 sine x cos x over 2, and the 2's cancel. So you could write this as 1/2 bracket x plus sine x cos x, if in you wanna, right? But I would accept this as your answer, of course. This would be fine. I want to show you the double angle thing to simplify at the end for a few reasons. First off, this is nicer, right? Clearly the sine of 2x, I would rather have sines and cosines of x because I started with like sines and cosines of x. Also, because of the nature of the double angle identity, sine 2x is 2 sine x cos x, the 2 will cancel after you apply that identity. So this just looks nicer to me. Finally, when we get to section 7.3, you will need to do this because we'll have steps to simplify remaining after the trig work. No, Kitty, I love you, Kitty. Sorry. All right, say hello to the terrorist. This is Nala. Yes, you're a terrorist, aren't you? You want to say hi? Hi. All right, now get the fuck out. I love that cat, but she is deeply irritating. Okay, so even powers, you're just going to use these identities. The cos squared equals 1/2 1 plus cos 2, or sine squared equals 1/2 times 1 minus cos 2, until you get to a place where you can figure out the antiderivative. And sometimes that's really simple like this, but other times it's more complicated, requiring multiple applications of those identities. So let me show you one more example. Again, anytime the powers are both even, this is what we're going to do. So let's do sine squared x times cos squared x dx. The difficulty kind of goes up with the sum of the powers. So if the sum of the powers is 4, that's harder than the sum of the powers being 2. If the sum of the powers were 6, then that's harder than the sum of the powers being 4, and so on. Again, both even, so half angles. Sine squared x is 1/2 times 1 minus cosine of 2x. Cos squared x is 1/2 times 1 plus cosine of 2x. And dx is still just chilling. I replaced both sine squared and cos squared by their half angle equivalents. Now I've got a 1/2 times 1/2 that can come out front as a 1/4. And then inside I have 1 minus cos 2x times 1 plus cos 2x. And the only thing I could hope to do here is FOIL this out. Right? I cannot integrate each of these separately because they're being multiplied. We talked about that when we talked about integration by parts. Can't split up integrals over multiplication, so you have to distribute everything out. In this case, that's not so bad because the cross terms are going to cancel. My firsts are 1, so I'll have 1, and then minus cos 2x plus cos 2x. I'll write it, minus cos 2x plus cos 2x. That are my inners and outers. And then my last is minus cos 2x times cos 2x. That's cos squared of 2x. And this is the term that's going to give us a bit of a headache. So the middle terms here go away. This is nice. Those add up to 0. So what I need to do is integrate 1 minus cos squared of 2x dx. The 1 isn't stressing me at all, right? Integral of 1 is easy. But the integral of cos squared of 2x, that is like a sine cosine integral where the powers are all even, right? This thing on its own is a bit of a challenge. And the trick is to take your half angle identity, which I will write here in terms of theta. Cos squared of theta is 1/2 times 1 plus cosine of 2 theta, and replace theta by 2x. Because what I have here is a cosine squared of 2x that I need to clean up. And if in this identity I plug in 2x for theta, then the left-hand side will become cos squared of 2x, which is good because that's what I need, the right-hand side will become 1/2 times 1 plus cosine of 2 times 2x, which is 4x. And sometimes I call this the modified half-angle identity. There's a bunch of ways to describe it. The upshot here is that in this identity, what matters is that the angle on the right is twice the angle on the left. So cos squared of 2x is 1/2 times 1 plus cosine of 4x. And that's down here what we need, right? So this is how you get it if you forget it, or if you need other variations on these identities. The thing is, yeah, it's an identity, so you can plug in whatever the hell you want for theta. That's literally what an identity means. So I'm going to plug that in, and I get 1 minus 1/2 1 plus cosine of 4x, close, 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 dx. I'm going to distribute that 1/2 and combine the constant terms. There are going to be some like terms here that can be combined. And then we'll be to a place where it's all micro U sub. So 1/4 out front, integral. Distributing this 1/2, I get 1 minus 1/2 minus 1/2 cosine of 4x dx, like so. No, kitty. Kitty. I love you, kitty. You can't be here right now. All right. So the 1 minus 1/2 here, those are both constants. They can be combined. On a good day, 1 minus 1/2 is 1/2. So this is 1/4 integral of 1/2 minus 1/2 cosine 4x dx. And now the hard work is done. Right now I've beat the thing to death. When I say beat to death with the half-angle identities, arriving at this is what I mean. It took 2 applications of half-angle identities. Right. First, I swapped sine squared and cos squared for their half-angle equivalents. That's one application. Then I simplified and I got to here. And I realized, oh shit, this is a cosine squared again. Well, the only way I know to integrate even powers of sine or cosine is the half-angle identities. So I better apply another half-angle identity to this thing. And that's what this is. This down here is the half-angle equivalent of cos squared 2x. And we got that by substituting in 2x for theta in the half-angle identity. So I got a question about the next couple lines down here. This is 1 minus 1/2 minus 1/2 cosine of 4x. So the third 1/2 is attached to the cosine of 4x. That came from distributing this negative 1/2 here. Oh, damn it. Shit. I have one of those days. Today is one of those days. Came from distributing this over those parentheses. So I've got a constant there. No, you're good, you're good. Now we're ready for our antiderivative. I've got my 1/4 out front. Antiderivative of 1/2 dx is 1/2 x minus antiderivative of cosine 4x is sine 4x over 4. I also have a 1/2 here. So 1/2 times sine 4x over 4 is sine 4x over 8. And then we add our plus c. We could then try to break this down using double angle identities. We can distribute the 1/4 if you want. I would just stop here. This is fine for the purposes of this problem. I think the tricky step is figuring out what to do after you get to this, right? The cos squared of 2x. And the crucial realization is that anytime you're trying to integrate even powers of sine or cosine, it just means half angle stuff. So you got to find some way to use this identity on this piece. And since it's a cosine squared of something, it makes sense to start with your half angle identity, which is cosine squared of theta equals blah, 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 and plug in for theta whatever your something is here. So if this was cos squared of 3x, I would end up with 1/2 times 1 plus cosine of 6x, just by substituting theta equals 3x in this trig identity. It's a trick you're going to need to master. There are problems, I think 1 or 2 like this in your homework. It's not that hard, but a little bit of practice. Make sure you have this nice and clean in your notes. Being able to look back at this will help a lot when you arrive at one of those problems and feel a little stuck. Is there anything we'd like to ask about here? That's okay if it feels a little overwhelming at first. Look at your notes. Make sure it's nice and clean and correct in your notes. Maybe take a screen cap so you can refer back to it in case there's an uncertainty or an error. I am going to move on now. One more thing before secant tangent integrals. We never talked about what to do if the powers of sine and cosine are both odd. These are more fun to do in odd numbered years. So let's pretend it's 2021 again. We said if one of the powers is odd, then you're going to grab a copy of the odd guy, set it aside, make a substitution for the other guy, right? Well, they're both odd here. So what do? I could follow that first strategy, thinking of either of these as the odd power. So there's 2 paths to a solution here. First path is treating sine cubed like the odd guy. So I'd write sine squared x cos 2021 x sine x dx. Treating sine like the odd guy, setting one of him aside. The other path is treating cosine like he's the odd guy. So I'll leave the sine cubed x alone and grab one of the cosines. So that'll leave me with 2020 of the cosines. And then a cos x dx here. In the first integral, the first setup, I'm imagining I want to substitute for cosine because I'm setting aside a copy of sine x to cancel with my du or dz. In the second path, I'm imagining that I want to substitute for sine because I'm setting aside a copy of cosine to cancel or be absorbed in my substitution as dz. Before I could execute either of those, I need to rewrite all the remaining powers. So here I want to substitute for cosine because I'm setting aside a sine. That means I need to rewrite the rest of these sines as cosines. So sine squared by the first Pythagorean identity is 1 minus cos squared, and then cos 2021 sine x dx. So this integral is now ready for the substitution z equals cos x. In the second integral, I'm setting aside a cosine, which means I'm thinking of substituting for sine, which means I need to rewrite all 2020 of these cosines as sines. Now there's a way to do that. I'm leaving sine cubed alone. Cos to the 2020 is cos squared x raised to the 1010. And then cos x dx is still chilling. And then finally, that cos squared is 1 minus sine squared. So this is 1 minus sine squared x, all raised to the 1010 times cos x dx. Now these are both ready for the appropriate substitution. In the first integral, I would let z be cos x. So dz is negative sine of x dx. And you see I've got my sine of x dx here ready to be soaked up or canceled by the dz. In the second integral, the substitution would be z equals sine of x, which means dz would be cosine of x dx. And again, I've got my cosine of x set aside at the end, ready to be canceled or soaked up in that substitution. In the first integral, dz is negative sine x dx. So this sine x dx, this would be negative dz. So this piece here would be negative dz, and the negative I can pop out. In the second integral, this is just exactly dz, which is nice and clean. So let's write down what we get. The first integral becomes negative from the negative dz, integral of 1 minus z squared times z to the 2021 dz. And the second integral would become integral of z cubed times 1 minus z squared to the 1010 dz. And I want you guys to tell me which integral is easier. Integral 1, or the first path, or integral 2 from the second path. Give you a minute. I do want feedback on this, so I'm going to wait for actual responses here. Yeah, I've got 1 vote for integral 1, 2 votes for integral 1. Yeah, all right. And I don't know if it's a bandwagon thing or if we're all seeing it. Either way, it's pretty good. Everybody seems to agree that the first integral is easier. Can somebody tell me why the second integral is harder? Why is it that we don't want to do this one? Yeah, it has something to do with this power. Now I've got a big ass power over here too. So why is this power bad news and this power not bad news? So we're correct that this sucks. We really don't want to do that. And it's not the parity. It's not the even or oddness. If this was, 1011, this would still suck. Because we'd have to multiply it out. or FOIL 1010 times, right? That's 1 minus z squared times 1 minus z squared times 1 minus z squared, so on, so on, so on, times 1 minus z squared 1010 times. No thanks. Right? In order to integrate this, in order to integrate a polynomial in general, it has to be in its expanded form, right? In order to apply that power rule, I have to have sums of powers of sums of powers of variables. Now it can be done using something called the binomial theorem, but it's horrendously nasty. Right? It really, really is. Like if this was a 2, I would be like, all right, that's 1 minus 2z squared plus z to the 4. That's not so bad. Then distribute your z cubed, then integrate. But it's 1010. So I don't want to do this. I don't think you want to do this. I don't think anyone wants to do this. This, on the other hand, the subtraction is over here where there is no power. So I can just distribute this z straight up over these two terms. I only have two terms here instead of what would be 1011 terms here. So this one becomes negative integral z to the 2021 minus z to the 2023 dz, which is an easy integral. It only has two terms. So it's negative z to the 2022 over 2022 minus z to the 2024 over 2024 plus a constant. And then distributing this negative and plugging back in z for cos x, that's negative cos 2022 of x over 2022 plus cos 2024 of x over 2024 plus a constant. Just to be clear, you could do this. And no one could stop you from doing this. You might get quite tired because it would take you probably about a month, but you could do it and you would get a big friggin' polynomial. And when you do that, you could integrate each of those terms, right? Distribute the z cubed over that big polynomial, then integrate each of those terms. And you would get an expression that is equivalent to this, but would have many, many, many terms. Whereas over here, because that big power is just attached to a z. It's not a binomial raised to that power. It's just a monomial raised to that power. The only algebra you have to do here is take this z and distribute it over this binomial, getting you this. So z to the 21 times 1 is z to the 2021. Z to the 2021 times z squared is z to the 2023. And then apply your power rule. So you add 1 to this power, giving you z to the 2022, and you divide by that new power. So in each of these guys, you're just applying the power rule to these guys. And the magic here is that with path 1, you end up with an integral at the end that only has two terms. It's a polynomial with only two terms. Whereas over here, you would end up with a polynomial, but it would have 1011 terms that you need to FOIL out before you can distribute and integrate. So yeah, fuck that noise. And the numbers here are just coming from the power rule. Just add 1 to the power, divide by the new power, just like integrating z squared gives you z cubed over 3. Just the numbers are much larger. So the purpose of this example is to illustrate two things. First, that when both of the powers, when you're looking at a sine cosine integral and both of the powers are odd, you can do that either way. you can treat either function as the odd-powered function. But really what you want to do is substitute for the larger power. All right, so if both of the powers are odd, you want to end up substituting for the larger power. So you treat the larger power as the even power and the smaller power, smaller odd power, as the odd power. So even if this was just like sine cubed times cos to the 7, you would want to go this way rather than this way, because this way you would have to FOIL out 1 minus z squared to the 6, which is still going to take some time. So if both the powers are odd, your goal is to substitute for the larger odd power, which means you're going to set aside one copy of the smaller odd power, rewrite the resulting things in terms of the other function, and then do that substitution. These make good exam questions. Hint, nudge, wink. Okay, that's enough sine cosine stuff. We've now beat to death every possible case there. So it's time to talk about secant tangent integrals. You may want to glance back at your notes from yesterday where I listed all of the identities we're going to use. We're still in section 7.2. This is the second half of 7.2. For the most part, these are the same sort of thing as the sine cosine integrals. What made the whole sine cosine thing work is that the derivative of sine is cosine, and the derivative of cosine is negative sine. So when you differentiate one, you more or less get the other. And any even power of sines can be written as cosines. Any even power of cosines can be rewritten as sines. The identities are all in Canvas under the review material. If you go to the Trig review under the review material module in Canvas, you can find the identities there. They're also in the previous lecture. I would get them from the previous lecture because that has just the ones that you need, right? Rather than a big list of all trig identities. So if you pull up the video from Monday, make sure you get those from the very start in your notes. All right, so what made the last stuff work is that derivative of sine is cosine, derivative of cosine is negative sine. So differentiating, they just swap back and forth. And even powers of one function can be rewritten as the other function. Some of that stuff is true about secant and tangent. Even powers of secant can be rewritten as tangents using the second Pythagorean identity. And even powers of tangents can be rewritten as secants using that same identity. The difference here, of course, is that the derivative of secant is not tangent. The derivative of tangent is not secant, but their derivatives are related to one another. The derivative of tangent is secant squared, and the derivative of secant is secant tangent. So the cases we break down into here if the power of secant is even, that'll be one of the cases. And if the power of secant is even, we're going to do some shit. Let's go ahead and write it. If the power of secant is even, what we're going to do is set aside a copy of secant squared with dx. If you take 2 away from an even number, you're left with another even number. So you'll still have an even power of secant left, right? The remaining, which will be an even power, right? The remaining even powers of secant. I'll say, right, the remaining powers of secant as tangents. Then we're going to sub z equals tan x. Sub for tangent. So if the power of secant is even, then the long-term goal is to sub for tangent. 2. The next case, if the power of tangent is odd. If the power of tangent is odd, and there's at least one copy of secant around, then you're going to set aside a copy of secant x, tangent x with dx and write. So you started with an odd power of tangent. When you set aside a copy of secant tangent, you're taking 1 away from that odd power. You'll have an even power of tangent left over. So write the remaining will be even powers of tangent. As secants. Then sub z equals secant x. There is a third case that is not covered here. So I'd like you guys to look at just the first clause of each of these cases. Under 1, it says, if the power of secant is even, blah, blah, blah. Number 2, if the power of tangent is odd, blah, blah, blah. What is not covered by those 2 cases? What case is missing? Well, if you're not in case 1, then the power of secant can't be even, so the power of secant will be odd. And if you're also not in case 2, then the power of tangent is not odd. That means the power of tangent is even. So the missing case here, if the power of secant is odd and the power of tangent is even, then we're a little bit fucked, frankly. Those are nasty, nasty, nasty integrals. Then you're going to do looping integration by parts. These are the hard ones. All right, everything else is easy. Everything else is U sub. You could technically do those in Calc 1 if you are sufficiently comfortable with your trig identities. This is the one case in all of these 7.2 integrals where you actually need a Calc 2 technique. And the technique is looping integration by parts. I'll show you an example of this third case of the secant tangent integrals. The classic is the integral of secant cubed. But in general, just straight odd powers of secant suck. They are like this, right? So the power of tangent is 0, which is even. The power of secant is 3 or 5 or whatever is odd. Anytime you have an odd power of secant and an even power of tangent, you're in for a ride. But yeah, in words, this is the strategy. This is how we do stuff. All that's left is to look at some examples. So I'll give you a second to write. Maybe I'll refresh my coffee and then we'll look at some of these. Okay. If you haven't finished copying, take a screenshot Remember, that's the print screen button on your keyboard. For me, it's function delete, but you should see one there somewhere that says print screen. Let's do it. Tan cubed secant to the 4. Which case am I in? Case 1, case 2, or case 3? Yeah, I got it in a DM. We're in the first case. The power of secant is even. So our long-term goal here, sub for tangent. What's required to do that? Well, the derivative of tangent is secant squared. So I'm going to set aside a copy of secant squared, just like we said. So what's left is tan cubed x, and then I have secant squared x times secant squared x dx. Let's take two of those secants and I set them aside with the differential dx because I'm planning to do this substitution whose differential dz is secant squared x dx. Before I can employ that substitution, though, I need to rewrite the remaining secants as tangents. So I have tan cubed x. This secant squared x dx is going to be dz, but this secant squared x needs to be rewritten as tangents. And the identity here, tan squared x plus 1 equals secant squared x. That's your identity. So that secant squared x, I'm going to write that as tan squared x plus 1. And the other secant squared x, I leave alone because he has been set aside with the differential for the substitution. This integral is now ready for that substitution because I've got my dz right here. And everything else is in terms of tangent, which is my new variable. So when I plug in that substitution, we get integral of z cubed times parentheses z squared plus 1 dz. Hopefully these substitutions are feeling more and more natural the more you do them. From here, it's an easy problem. Distribute the z cubed. Z cubed times z squared is z to the 5. Z cubed times 1 is z cubed. And now you have a polynomial in its expanded form. You can integrate that using the power rule. That's going to give you z to the 6 over 6 plus z to the 4 over 4 plus a constant. And finally, you can plug back in tangent x for z. So this is the 6th power of tangent over 6 plus the 4th power of tangent over 4 plus c. A quick note, people have a tendency to get sloppy and stop writing the variables inside the trig functions. It's just coming to mind now. I'm imagining grading your test in the future. Do not get sloppy. You need, every time you write a trig function, every single time, you need to write the inside as well. So tan cubed on its own doesn't mean shit. Tan cubed of x means something. All right, so do not write tan to the 6 over 6. It's tan to the 6 of x over 6. Make sure you're always writing your variables. Never, ever, ever leave that shit out, please. I will take points off on the test for that. All right, questions on what we did here? Dogs barking. Questions going once? Going twice? Let's see. Yeah. Oh, that's interesting. I hadn't thought of that. Yes, you're correct. So the power of tangent here being odd means we could also have used the second rule. Those are not mutually exclusive. So the power of secant was even. It's also true that the power of tangent here was odd. Oh, let's work that way. The next thing was going to be an example of that sort of thing. Let's see it. So the long-term goal, when you're thinking about case 2, is to substitute for secant. We say if the power of tangent is odd, then you're going to set aside a copy of secant tangent to enable you to substitute for the secant function. So if we approach that like this, I do have a copy of secant tangent I can extract, and I am, when I do that, left with an even power of tangent because the power of tangent at the start was odd. And then I can take those remaining tangents and rewrite them as secants because tan squared x plus 1 is secant squared x. That means tangent squared x is secant squared of x minus 1. So you have secant squared minus 1 times secant cubed times secant tangent. And while I'm not saying the variables, I am writing them, and you always should do that as well. So this integral is now ready for the substitution. C equals secant x. dz then would be secant x tangent x dx. Integral becomes integral of z squared minus 1 times z cubed dz. Which is slightly different than the integral we got last time. But we would expect it to be different because we're subbing for a different function. The idea is that with these trig identities, there's multiple ways of writing any function. So if I carry on here, distributing the z cubed, I get the integral of z to the 5 minus z to the 3 dz. And that would be z to the 6 over 6 minus z to the 4 over 4 plus a constant, which would be the 6th power of secant x over 6 minus the 4th power of secant x over 4 plus c. Back in the day, when I took Calc 2, we didn't have WebAssign. It wasn't a thing yet, thank fuck, because I would have hated it. God, I don't know if I would have made it through college. I don't know how you guys do it. Back in the day, what we did is we got assigned a shitload of problems from the textbook, and if you wanted to know if you did it right or not, you looked in the back of the book, and it had the answers to the odd problems, so you could only check half your problems, but it was whatever. This was a pretty common thing, where you're like, the book says this, but I got this. And they're supposed to be the same integral. So did I fuck up? Now, there are no mistakes in either of these. But certainly secant to the 6 over 6 minus secant to the 4 over 4 looks different than tan to the 6 over 6 plus tan to the 4 over 4. If you want to know, are these both correct? What you can do now, I mean, again, you won't be bothered by this because your homework will just be like, yeah, it's correct, good. But the thing that we used to do if we were absolutely stuck is you'd use your graphing calculator to graph both answers. Now, you don't necessarily expect them to be identical, but you do expect them to be vertical translates of one another. Oh, Desmos doesn't like this. Yeah. Gotta do it like this. All right. So here's the answer we got by substituting for secant. Here's the answer we got by substituting for tangent. And they're not the same, but they are vertical translates of one another, which is what you want, right? Like the integral of x squared this is one valid answer. This is another valid answer. And they are vertical translates of one another. So as long as your answers are vertical translates of one another, then they could both be answers to the same integral. Or as long as your answer is a vertical translate of the answer in the book, your answer is correct. So while these two are not identical, you could use trig identities to transform this into this plus 1. That's what's going on here, right? If I shift, oh, it's not 1, it's some other constant. Yeah, I wonder what that constant is. It looks like it's actually quite small. I bet it's 1/24. Is that it? No, still too high. Yeah, I'm not sure what it is. Anyway, they're vertical translates. So yeah, equivalent as answers to integrals because of the plus c. But this problem could be attacked either way. Lives in both worlds. The power of secant is even, so you can set aside a copy of secant and substitute for tangent. Also, the power of tangent is odd, so you can set aside a copy of secant tangent and substitute for secant. And both will get you a correct answer. I'll do one more of these. So I don't like the idea of using the same example for both and not doing anything else. This last one is actually requires a bit of creativity. We talked about how to integrate tangent the other day. That was one of our little preliminaries. And now in theory, we have all the things we need to integrate any power of tangent times any power of secant. Tan cubed. So the power of tangent here is odd. Now the power of secant here is technically even, it's 0, but I don't have 2 copies of secant that I can set aside. And I also don't have a copy of secant squared I could set aside, right? I don't have a secant squared, and I don't have a secant to make a secant tangent to set aside. So this one is kind of fun. It's not obvious what to do here. It doesn't fit neatly into our strategies. Anybody have an idea? Yeah, technically this fits into the case design for rules 1 and rule 2. But the obvious strategy for either of those won't work because there aren't any secants to play with. Both rule 1 and rule 2 require setting aside some amount of secant, either a secant squared for rule 1 or a secant tangent for rule 2, but there is no secant here. Yeah, the correct answer came in the form of a DM from Fabrice saying, well, what if I think of tan cubed as tan squared times tangent? That's the sort of thing we've been doing. And maybe that will help. Why is it nice to have a tangent squared? Why do we like even powers in general? What do we do with the even powers most of the time, all through this section when we see them? Yeah, exactly. So Fabrice killing it in the DM. Sorry if I'm calling you out, but it's very nice. I feel you deserve credit. The real magic in all of these are these identities. Right? Over and over again, we're employing one flavor of these Pythagorean identities or another. This tangent squared, I can rewrite as secant squared minus 1. And then I will have secants and tangents to play with, which is what I like. So these functions all have personalities. Secant and tangent are assholes on their own, but when you get them together, they kind of cancel each other out and they're a little more chill. So I don't like hanging out with tangent on his own. He's a dick. Don't really like hanging out with secant on his own. He's not super chill either. But you get them together and they busy each other. Right, so they're not able to really do too much damage. Everybody has friends like that, right? So now I've got secant and tangents. The party is a lot more relaxed. I can distribute this tangent over these parentheses to get the integral of secant squared x times tangent x, and I'll write that as its own integral, minus the integral of tangent x dx. So distribute the tangent and split it up. All right, so when you distribute tangent here, you get secant squared times tangent minus tangent, and then you can split that integral into these two. This one is now a little straightforward U sub. This one is one of our preliminaries from last time, right? Everybody remembers the integral of tangent is the natural log of secant. So in the first integral, we sub z equals tan x. dz is then secant squared of x dx. And this guy is just, this negative is the negative above. This guy is just the natural log of secant x. He's one of our basic integrals. Known antiderivative. You don't have to show work for the integral of tangent. That was one of our preliminaries. The first integral, so what do I get all together? The secant squared of x dx, that's dz, so this just becomes the integral of z dz, and then I have minus the natural log absolute value of secant x plus c. So I get z squared over 2. I'm not going to write a separate plus c, minus the natural log of the absolute value of secant, constant, and that is tan squared x over 2. natural log of the absolute value of secant x plus a constant. Not bad. Okay. So those are the nice cases. If you want to come back here and add something to this page, you can, right? Namely, to the power of tangent is odd. If the power of tangent is odd, and there is at least one secant, right? Because in order to set aside a copy of secant tangent, you need a secant. So if you have just a pure odd power of tangent, you handle that the way we just did. You grab off a tangent squared to rewrite as secant squared minus 1, and then you can start doing stuff. So in order to get started with the second case thing, not only does the power of tangent need to be odd, you need to have at least one copy of secant. Okay. So you've seen some case 1 and case 2 integrals. They're not that bad. They're very similar to the sine cosine integrals, where you do some trig, you do a u sub, then you're dealing with a polynomial. This is the only case where you cannot work the integral down into a polynomial. No matter how much u sub you do, no matter what trig identities you do, you will never turn an odd power of secant into a polynomial in tangent, or vice versa. The classic example here, secant cubed. My Calc 2 professor said this integral is going to make you cry. He also said this integral is going to be on the test, and many, many, many people were unable to get it on the test. So let me tell you, this integral is going to make you cry just a little bit. This integral will be on the test. Can't be a whole lot more straight up than that, right? The power of secant is odd. It's 3. No, I promise I don't hate you. There are good reasons why this is an important integral, not just because it's challenging. The real reason this is so important is because this integral shows up all the fucking time in physics. Odd powers of secant, for whatever reason, show up all over the place in physics. So, also number theory, right? My own native land. Power of secant is odd, power of tangent is even. That means we should do some looping integration by parts. We're given no more guidance than that. So we trust the guidance we have. This is case 3. So we're going to do some sort of looping IBP, which means we need to select U and dv. Now, I say with love that this is going to be on the test, right? I want you to be warned so you know to prepare yourself. Ethan Klein style, peace and love. So nobody told us how to choose U and dv for this. Everything here is trig, so LIPET doesn't help either. So this is where thinking of things the way Arthur Matic thinks about things. Remember that MIT guy I mentioned when we talked about integration by parts? He says, look at your integrand for a piece that you would like to integrate and a piece that you would like to differentiate, right? You should choose for U something that is nice to differentiate, and you should choose for dv something that is nice to integrate. So when you're looking at this secant cubed, it's either secant cubed times 1 or secant times secant squared. Those are the only ways you can partition. Which of these things is nicest to integrate? Secant cubed, secant, or secant squared? which of those things should I pick for dv? Very good. Yeah, getting flooded in the chat here with secant squareds. I know how to integrate secant squared, and it is nice. I also know how to integrate secant. That was one of our preliminaries last time, but it's not nice. It's the natural log of secant plus tangent, and I don't want that showing up later in an integral. The integral of secant squared is just tangent. I'm not afraid of that. So here's the choice. You're going to pick for dv the thing that is not scary to integrate and yields a nice thing when you do integrate it. That's secant squared. And you're going to pick for u the other stuff, which is just secant x. This means that du is going to be secant x tangent x dx, and v is going to be the integral of secant squared, which is just tangent. So this is the setup for our integration by parts. The good news is, while this is a looping integration by parts problem, you're only going to need to do IBP once. The way we get it to loop is by applying trig identities after this. So the integral of u dv is u times v, that's secant x tangent x minus the integral of v times du, that is tangent x times secant x tangent x dx. And this integral is not so great. It's not so great. If you combine these, this is secant times tangent squared. So again, odd power of secant, even power of tangent, that's the case 3, the alarm bells go off. But let's just write it down in that form and try to think what not horrible stuff we could do to it. Remember, I promised only one run of integration by parts here. These looping integrals are easier than the damped harmonic oscillator. They only require one IBP. The thing that replaces your second IBP to make the integral loop is a trig identity. So tan squared of x there I will replace by its Pythagorean equivalent. Tangent squared is secant squared minus 1. Now I distribute this secant. You see, we're very close to getting this to loop. My original integral is secant cubed. When I distribute this secant, I will get secant cubed of x minus secant of x. And I'll split that up. Actually, I'll do it in separate steps. This is more writing than you need to do, but people always lose a negative sign when I don't show this, so. So I get minus the integral of secant cubed x minus secant x. Now in this next step, I'm going to do two things. I'm going to distribute this negative. So I'll have negative secant cubed plus secant and split up the integral. So this is secant x tangent x minus the integral of secant cubed x dx. That's the negative secant cubed here. And then this negative hits this negative and makes it a positive. So that's plus secant. So I'll have plus the integral of secant x dx like this. Here's your original integral. We have successfully gotten this integral to loop. There is this straggler bit here, though. But this was one of our preliminary integrals. The integral of secant, remember we did on Monday, is the natural log of secant plus tangent. So what I get here, let me write it in a single line. I have the integral of secant cubed x dx equals secant x tangent x minus the integral of secant cubed x dx, and then plus this piece, which is the natural log of the absolute value secant x plus tangent x plus c. I'll go ahead and write the plus c now. Why not? So the integral I started with is equal to secant tangent minus the integral I started with plus the natural log of secant plus tangent. So if you add this integral to both sides, you get 2 times the integral of secant cubed x dx, or 2I, if you like that notation where you write I equals blah minus I. You get 2 times that integral equals secant x tangent x plus the natural log of the absolute value of secant x plus tangent x plus a constant. And now you can divide both sides by 2 for the win. So the integral of secant cubed x dx, I'll write it as 1/2 secant x tangent x plus the natural log of the absolute value of secant x plus tangent x plus a constant. I need to close that parenthesis x. It's not a small amount of work. And I don't mind telling you that while this integral will be on the test, it will be a variation on this, like maybe secant cubed of 2x, or maybe cosecant cubed of x. And it will be in a problem that has an element of choice. Like I'll give you a couple of integrals to choose from, and I'll say, evaluate one of the following looping integrals. Probably one will be a damped harmonic oscillator, some choice of those constants a and b. The other one will be one of these trig looping integrals where you've got an odd power of secant and an even power of tangent. There are, I think, just one of these in your homework. I think I gave you secant times tangent squared, which is done the same way. Integration by parts, choosing u and dv in the fashion I did here. Not the same choice of u and dv, mind you, but with the same logic. Run IBP once, and then apply a trig identity to get it to loop. We are just about out of time for today. I want to take a second for any questions on this. Okay, and I do want to introduce the concept of section 7.3 before I let you go, because it's a little tricky. Seeing it ahead of time will help. So that's the end of 7.2. You guys can now integrate any trig function in the world. Seriously. So here's our intro to Trig Sub. Back in Calc 1, especially if you took Calc 1 with me, you did the integral from 0 to 1 of the square root of 1 minus x squared dx. If you don't remember, that's okay. But I'll tell you that you did it before I showed you the fundamental theorem of calculus. In other words, you solved this integral not by finding an antiderivative, right? Not by like integrating this function and then plugging in bounds. You did something else. You did this by thinking about areas. Because the function you're integrating here, y equals the square root of 1 minus x squared, is secretly the same thing as y squared equals 1 minus x squared, which is not so secretly the same thing as x squared plus y squared equals 1, which is the unit circle. So the way you did this is a problem back in section 5.1 of the textbook, the section on areas and distances. Here's the point 1, 0, right? Here's the point 0, 1. This circle, the unit circle, is x squared plus y squared equals 1. So what you're trying to integrate is that function, or really the positive version of that function, just the upper semicircle, from 0 to 1. So you did it by finding this area which is 1/4 the area of the circle. And the area of a circle is pi times the radius squared. The radius of the unit circle is 1. So this is 1/4 pi, or pi over 4. You could not, at that stage, do the indefinite integral. And I'm not going to do the whole integral here for you today because we are over time. But I'll tell you that the trick to doing this integral is something very similar to this. What you're going to do is let x be sine of theta. Now, of course, that means dx would be cosine of theta d theta. This is a substitution, but it is kind of a backwards substitution because your new variable, which is theta, is over here inside the sine function on the right-hand side. Normally, we would substitute like z equals x squared or z equals 1 minus x squared. Your new variable is a function of the old variable, usually. these substitutions are backwards in the sense that your old variable is a function of the new variable. This makes life easier. This is a good thing, because now instead of having to look around for something that you can pair with the dx or cancel with your du, you just get dx equals cos theta d theta straight up in terms of the new variable. In other words, we're not going to try to cancel anything with my differential. We're just going to plug in for my differential. But the real reason this is nice, right? That's why these substitutions are easier to execute. But the real reason this is nice is because then the square root of 1 minus x squared will be the square root of 1 minus sine of theta all squared, which is sine squared theta. And sine squared theta, following those same identities we used all through 7.2, is cos squared theta. Now, we've said a bunch in this class that you cannot split square roots up over addition and subtraction. The square root of 1 minus x squared is not 1 minus x. What this identity does, 1 minus sine squared, there's still some subtraction under the square root, which means I still can't give the square root to those things separately and clean it up. But that identity turns those two terms into one term. The square root of cos squared theta is cos theta. So we get rid of the square root. So this integral becomes the integral of cos theta, that's from the square root, times cos theta d theta. This piece coming from the square root, this piece is dx. And the magic is that this is now the integral of cos squared theta d theta. So what happened? Well, my square root went away. That's the big thing. What makes this integral hard is the square root. And because of these trig identities, or this trig identity, 1 minus sine squared theta equals cos squared theta, we're able to simplify the square root. I can write that difference of two terms as a single term, which I'm then allowed to take the square root of. And now what you have is a perfectly reasonable 7.2 integral. It's an integral of a trig function, just a straight up power of cosine, half angles, blah, blah, blah. So now you use 7.2 methods on this. And this is what we're going to do all through section 7.3. We're going to take these integrals that have gnarly square roots. We're going to make a little substitution here where you bring in a trig function, and that's going to turn your integral with gnarly square roots into a nice integral with no square roots, but lots of trig. And the important thing that I want baked into your head today is that the square root of like a squared minus b squared is not a minus b. We can never do that. So you can never split up square roots like this, right? The square root of a squared plus b squared is not a plus b. So to get rid of roots, with addition or subtraction in them, we need trig sub. We need to be able to turn things like 1 minus x squared into a single term. And that's exactly what the Pythagorean identities do. Tan squared plus 1 equals secant squared. 2 terms, 1 term. 1 minus sine squared equals cosine squared. 2 terms, 1 term. Secant squared minus 1 equals tangent squared. From 2 terms to 1 term. So what we're going to do is I'm going to give you a big, like a, not a big, a 3-row table with one of the columns being square roots, right? If you have a square root that looks like this, you'll make a substitution like this. And then there's 2 other ones. We'll practice this a whole bunch next time. For now, I want you to finish up all of these 7.2 problems in your homework. Between now and Friday, I want you at least 90% done with all the straight trig integrals there. You can attempt some of the trig sub stuff if you want. That's any problem that starts with 7.3. You see the problem numbers next to them there. But I don't expect you to do any of those before Friday. Next class, I will solve the rest of this integral. We've already seen how this guy starts. And then we'll look at a whole lot more. So it would be very, very wise to do as many of the trig integrals as you can between now and our next meeting. And maybe also, I know this isn't something anybody ever wants to do in a math class, maybe also read the book a little bit. Because Trig Sub tends to be one of those sections where people have a hard time. And I don't want you to have a hard time, right? Here's the table with the different square roots and the substitutions you will make and the identity that makes them work. Maybe take a look at 1 or 2 of these things. Read the words in here. That way it's not all new and scary when you see it in class on Friday. All right, I'm going to let you guys go here. Thank you for sticking around. I know we went over time quite a bit. That's it from me. I will see you all on Friday.